Welcome to the CFE Media and Technology Education session, Understanding Total System Efficiency for Motion Control. I'm your moderator, Mark T. Hosky with CFE Media and Technology. In keeping with RCEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to understand motion system efficiency. Understanding efficiency details helps with component selection, system integration, installation, operation, maintenance, and other issues in the motion control system lifecycle. Here's a list of learning objectives. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen. If you'd like to take notes within the session, click on the left panel labeled Notes to do so. Question and answer session with an industry expert starts right after the live presentation. And you can see the Q&A details in the Meetings tab on the left side of the screen. Zoom invite details can be found in the Additional Resources tab under the Q&A session. You want to take the session again? No problem. The session will be available for on-demand viewing. If you're experiencing any difficulties, please log out and back into the session to continue. Finally, achieve a continuing education credit by passing the final exam at the end of the session. Here's some information about obtaining the approved PDH for today's session. Today's speaker is Jason Oakley, Corporate Trainer with SEW Eurodrive. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology. Jason Oakley is a corporate trainer at SEW Eurodrive's U.S. headquarters in Lyman, South Carolina. He earned a Bachelor of Science degree in Electrical Engineering from the University at Buffalo in 2013 and began his career as service engineer for a small local company in his hometown of Buffalo, New York. Upon relocation to Greenville, South Carolina in 2014, he began work as an electronics product and application engineer for SEW Corporate Electronics Group. For nearly 7 years, this is where he specialized in SEW's newest electronics product line, MoVC Modular Automation System. While working in parallel, Jason obtained a Master's of Engineering degree in Industrial Engineering from Clemson University in 2019. With a recent role change to corporate trainer, his shifted his focus toward sharing and teaching information he learned in academia and from real-world experience to help further develop SEW employees into greater value-added resources. On a personal level, he enjoys spending quality time with his wife and 2 young children. A die-hard Buffalo Bills fan, Jason has a passion for all things sports. He coaches his kids, follows his favorite teams, and participates in local ice hockey leagues. Jason, please go ahead.
Good morning to you all. Today I would like to talk about efficiency and how that relates to a system. I think it's an important topic to discuss, and now more than ever is becoming increasingly more relevant in industry due to its part in the total cost of ownership. Total cost of ownership is not just a buzz phrase. It's a philosophy for creating a sustainable business model in today's environment of shrinking resources and increasing energy costs. Every system has some degree of inefficiency. No single component within a system is 100% efficient. Converting some of intended work output to heat is a necessary evil of any process. However, the amount of heat or wasted energy created by a process can be minimized through thoughtful and careful selection of individual components. I would like to take a look at a few different ways in which we might be able to improve our total system efficiency. But in order to do that, we will need to define a few terms. I want to first start with discussing power loss, efficiency, and what a system is. I can then move into different components of a system and share a little information on how we might be able to improve efficiency within each of those components. We will start with our electrical power and move through the variable frequency drive, motor, gearbox, and finally to our transmission element. I will pull it all together in the end with a quick real-world example that will help to solidify all the concepts that we discussed here today. So let's get started. First, we need to understand what is power loss. So I like to think of it like this. We have a certain amount of energy going into a so-called black box system. It doesn't really matter what that system is, but we have some energy going in and we have some energy coming out, or power going in and power coming out. The amount of power or energy that is lost, that is an inefficiency. In every system, there's going to be inefficiencies, but what we want to do is figure out ways we can minimize those inefficiencies or power losses. So in our formula, power loss can be defined as the result of our input power minus our output power. If we manipulate the equation, another way we can look at this is our power loss, or power loss is our output power is equal to the input power minus our power losses. And we'll use that equation here in a minute to kind of shed some light on different things we can think about with efficiency. With regards to power loss, our efficiency is a ratio of the output power to the input power. And efficiency is a good measure of how well our input power is utilized in our applications. You will want to limit the amount of power that's needlessly turned into heat and not used for good in your application. And by doing so, you will increase your efficiency. And just a little FYI for the rest of the presentation, I'm going to be using this Greek letter eta as our symbol for efficiency. So that's what it's looking for. That's what it means. So like I said, if you can take these power losses and reduce them or minimize them, we can increase our efficiency. And that's really the goal here. Determine what power is being lost, how is it being lost, and how can we minimize it or get rid of it. And that's what we're going to be taking a look at today. And we're going to be taking a look at that and how it's affected in a complete system. And we're going to be looking through that system piece by piece. So I think commonly people can think of a system as maybe a motor or a gearbox or a motor and a gearbox. But for me, I like to think of a system as a complete package. This includes the input power, a variable frequency drive, or an automatic speed drive or inverter. It has many names. The output of that VFD leads to the motor. That motor turns. That motor might turn a gearbox, and then the gearbox can turn a transmission element like a chain or a belt, or it can be directly coupled to your application, which could be a conveyor or a hoist or something like that. This is an entire system, and we're going to break the system down into its individual components, see where we're losing power, and how we could possibly improve upon that. But before we do that, let's take a look at where we can save some energy, where the most potential is to save some energy, so we can kind of have an idea. Take a look at these three main areas for improvement. First, we have potential using high efficiency motors or a premium efficiency motor. Next, we can introduce VFDs into our system. This allows us to control the speed of the motor or vary the speed rather than running it directly off the mains. And lastly, we have mechanical components that have a large potential for improvement. We'll save some energy within all three of these areas, but by far the largest impact that we can make is with optimizations of the mechanical components. Every system has different components, like we've mentioned. We've been talking about this for a couple minutes now. You have your input power, your variable frequency drive, your motor, your gearbox, and your transmission element. And then you have your load or the application that you're trying to move. Each component has losses. Nothing is 100% efficient, and definitely nothing is greater than 100% efficient. But what's really interesting is how these efficiencies relate to each other. The effect is actually multiplied. So each little inefficiency is multiplied throughout the system. So you can have a really good high efficiency motor that is directly coupled to your load. But if you have a poor efficiency gearbox in between there, you lose all the benefits of buying that high efficiency motor. So that's something that we need to take a look at and try to fit into the big picture of our system. Look at all the individual components and see if do they make sense adding them together. Well, not adding together, but multiplying them together. Just for example, if we looked at an ideal system where every component was 99% efficient, if we had our 6 components here, they're all 99% efficient. When you multiply those together, our maximum efficiency of the system is only 94.15%. That's throwing almost 6% of our power just to energy losses. We're kind of throwing that out because it's burned off as heat. And that's an ideal system. That's very efficient, and you're probably never going to see something like that. Now, if we look at a typical system, which I've selected some really good efficiency components here, actually multiplying these together, we see almost 80% efficiency. And that's pretty good, but you can see the difference there, a real world versus a perfect situation. But one of the things you can think about is you can eliminate some of those components maybe in between there. Maybe you don't need a transmission element. Maybe you don't need a belt to couple the gearbox to your conveyor. If we get rid of one of those elements, you can get rid of some of the inefficiencies, and that would make your entire system a little bit more efficient. So now let's take a look at each of the components that make up our system. And we're going to start with the electrical power. This is the electrical input that feeds the inverter or to the motor if you don't have an inverter, and it's going to have some losses. If you look at the diagram, we have our power in, then several different power losses, and then finally our power out. So you're going to have some copper losses, you're going to have some reactive power losses, and even some harmonic losses. One of the main losses that we're going to concentrate on is reactive power, and that's because that's something that we can actually do a little something to kind of help out and minimize those losses in our system. But another loss in electrical power systems that I want to address briefly is the copper losses. And that's the amount of heat that's created when the current flows through your wire and heats up. The heat is lost energy and could have been used somewhere else. So one way you can minimize those copper losses is by selecting proper cable sizes. If your cable is too small, it increases the resistance, and that's going to increase your copper losses. So it's why it's very important to select the proper size of wire, proper gauge wire. That's just automatically just going to help us be more efficient. So let's get into the reactive power that I just mentioned. Before we do that, we'll have to kind of discuss what electrical power actually is. Well, it's the product of voltage times current. And if you look at the picture here, you can see when the voltage and the current are in phase, and by in phase, I mean they go up and they go down at the same time. They both cross the same point on the x-axis simultaneously. And you can see that's the case with this particular example. When that happens, all of the power is positive. And that means all of the power is being used by the load. And that's a good thing when your voltage and your current are in phase. If they are not in phase, the difference between those is called a phase angle. And this can also be thought of as a power factor. I know some of you guys might have probably heard of power factor. That's kind of what it means. The voltage and the current are out of phase with each other. And what happens here is when you consider the electrical power of a system that has the voltage and current out of phase with each other, when those are multiplied together, a positive times a positive is a positive, so that's good. And the negative times a negative is a positive, so that's also good. But when you have a positive times a negative, it makes a negative. And when we have a negative power, that is power that is lost and is returned to the line. And that's an inefficiency for you as the end user of electrical power. So what can we do about that, and how can we correct that? Well, we're concerned about that phasing, like we mentioned. How can we get rid of that? Where did it come from, and why do I have a phase angle, and how can I kind of reduce that or minimize that? If we think about it in relation to a power triangle, there are different types of electrical power. We have real power, and that's actually that's what's really doing the work. That's your kilowatts or your horsepower. That's your real power rating. You also have apparent power, which is basically what you're paying for when you have an electric bill. You're paying for the apparent power, the amount of power that the power company sent to your house. And that's how much you're paying for. If you have reactive power, well, guess what? That contributed to your apparent power, but you weren't able to do any work with it. It was just reactive power. The reactive power, we want to minimize that the best we can and make our apparent power equal to our real power. That way we're getting our money's worth and minimizing our waste. Generally speaking, we have one of two types of loads when looking at our power triangle. You can have a capacitive load where the power factor is actually leading a little bit, and that means the load current is leading the supply voltage. But this doesn't happen too often in our industry. It could potentially happen sometimes with inverters, but you'll typically find capacitive loads in like radio circuits or electric motors, and some computers and power supplies. Typically, the electric loads that we are dealing with in our industry are inductive loads, like a motor, for example. That simply means that the load current lags behind the supply voltage. And FYI, lightning bolts, believe it or not, are actually inductive loads. The majority of industrial loads are going to be inductive. So our power triangle is going to look like this, and we're going to be kind of dipping below the x-axis. So now, finally, to the point, how can we minimize that reactive power? Well, if our power triangle is going below the x-axis, like the inductive load, what we can do is add some capacitance to it. So we have this power triangle with our reactive load. If we want to minimize that reactive power and minimize our apparent power, which would in turn minimize the amount of energy that's not being utilized properly, we can add some capacitance to the system. And these are called power factor correction capacitors. You may have them in your plant, and that's what they do. They minimize the phase angle difference between the voltage and the current, trying to make the most of the power positive and being used by the load as real power. So that's one way we can help out with our efficiency by minimizing our power factor on the electrical side. Ideally, our power triangle would actually be a straight line with no reactive power. In that case, our electric bill would be for work done, and it would not include any waste. Now that electric power we just talked about, that's going to feed our inverter, and that's going to be the next part of our components that we're going to discuss. Now, a lot of people are under the misconception that if you add a variable frequency drive to your system, you're automatically more efficient. But that's not necessarily true. If you take an existing system, you don't change anything else, and all you do is add a component to it. It doesn't matter what component you add. There's going to be an inefficiency that you're adding to the system that gets multiplied through your entire system, and you're going to be losing energy. A VFD doesn't magically operate without any power loss. Of course, there are power losses inside the VFD. They get hot when they run, so you know that there's some of that energy is being transferred into heat and not being used 100% efficiently. But you do stand to make some other gains when you add a VFD. So we'll talk about those different things and how you can save energy in your system by introducing a VFD into it. A VFD has some losses, as almost any electrical component will. There's going to be copper losses. Everything that's electrical has copper losses, and that occurs when current travels through wires, or in this case, through the traces on the circuit board and create heat. That's lost energy. There are switching losses, and that's a little bit different. Within a VFD, we have output transistors. They turn on and off, and that's going to allow for some losses. And a little lesser known fact is that inverters also introduce some harmonic losses to the motor that actually decreases the motor efficiency. So we'll talk about how those affect the overall system as well. If we look at the basic parts of an inverter, we have our AC power that's coming in, that goes into our input rectifier, and that gets changed to a DC voltage. And the control electronics of the inverter actually sends out DC pulses to the motor. And if you look at the output of the inverter, you can see the little black boxes. Those are actually DC pulses created as a result of opening and closing the transistors very, very quickly. And then we have this red line, which is actually the average current level of those pulses. So the black boxes are the voltage pulses that are coming out of the inverter, and the motor interprets those pulses like they are the sine wave that's in red that you can see there. The different sections of the inverter are all going to have different types of losses. The input rectifier, you're going to have some forward biasing power losses. You're also going to have some of those losses in the output section, but the main loss of the output section is going to be those switching of the transistors. They're turning on and off, they're going to heat up, and every time you turn them on and off, you're going to lose some of that energy. And those losses can actually vary because you can change your switching frequency and how fast you turn your transistors on and off. And you may have heard of like 4 kilohertz or 16 or 32 kilohertz switching frequency. That's what they're talking about. How fast are those output transistors turning on and off? And I'm sure you can imagine the faster the output transistors cycle, the faster that they open and close, the more energy that they're going to lose in the form of heat. Now that third section of the inverter, or the controlled electronics section, that also has some losses. That's kind of like the brains. You have the processor inside of there. You have resistors, you have inductors, capacitors, LEDs. There's all of these different components inside. They also have switch mode power supply that makes 24 volt easy to control everything. All these components use energy. All these components are going to create a little amount of heat, But if you have hundreds of these tiny little components, they all add up to some energy loss, whether it's 1 watt or 2 watts, it still has to be taken into consideration. So there are losses inside of the variable frequency drive. But usually variable frequency drives are very efficient, relatively speaking, 92 to about 98%. The efficiency of variable frequency drives actually depends on its power rating. Because we have those losses that we just discussed in the control section, basically the computer part of the inverter. As the inverter gets bigger or larger and larger, the output section is what's actually changing and accounts for the bigger portion of the VFD. Control section stays the same size, while the power section increases, meaning the losses become smaller and smaller the bigger the inverter gets. Remember I mentioned adding components to the system makes it more inefficient by default. But when you add a VFD, this is still true. However, there are some things a VFD brings to the table that can help increase in other parts of the system. And we'll talk about those very, very soon. A few other losses I talked about with the VFD. It might make your motor more inefficient. It's going to create some harmonic losses that I mentioned on your motor. What an AC induction motor wants to see is a perfect sinusoidal voltage. It wants to see that sine wave that you're used to seeing, that red image up there in the top. But these pulses from your transistor, it actually creates harmonics. These harmonics can add losses into your system, and it depends on the pulse signal. It also depends on the switching frequency and the pattern. But we'll talk about that in a little bit when we talk about the motor. But we can have losses up to 10% in the motor due to these harmonics. Another potential for power loss is in the cable going from the VFD to the motor. And that's something called parasitic capacitance. It sounds fancy and important, but it's actually really easy. And it's also more of a problem when it comes to electromagnetic compatibility or your EMC problems. But as the frequency of your signal gets higher, the impedance of your cable goes down because the cable actually starts to act like a capacitor with the cable conductor in the middle. So you can see in this picture that the rubber sheathing around the cable acts like a dielectric of a capacitor. So in between your power cables, it kind of acts like a capacitor. And in between the power cables and the ground, that also acts like a capacitor. So you can have some of these losses there. More importantly though, you need to pay attention to that because it has some electromagnetic compatibility issues and that might interfere with some of the other components you have in your plant. But it could also add some power loss to the system. So let's just review. There's kind of a lot of things we discussed, some of the VFD power losses real quick. First thing I mentioned, or one of the things I mentioned was we can have harmonic losses in the motor up to about 10%. We can have some cable losses in the inverter to the motor. We talked about that just now, parasitic capacitance. It can be roughly 4%. And the inverter has some losses. So there are losses when you add a VFD to the system. But oddly enough, in the cable between your supply and the inverter, you can actually gain some energy there. Remember we were talking about the power factor earlier. If you directly run your cable to the motor is very inductive load. There's going to be a huge phase angle there. They're a big power factor, and you're going to lose some energy there to reactive power. With an inverter, it's like an automatic power factor correction. It actually has slightly leading power factor. And so you can save some energy. You can actually save up to 20% of your losses on the cable in that portion of the system. So that's actually a gain that you automatically get by putting an inverter in. Now that doesn't outweigh all the other losses we discussed when you get a VFD, but there are some things that we can still do to save energy and make it worth it to add that VFD to your system. One thing I want to compare real quick is an inverter to a mechanical variable speed control. Because although this technology is a bit older, there's still a lot out there. There's still a lot of people asking for these and still a lot of people that use them. And this is the type of control that they use to vary speed without using a VFD. There are a couple different types. They have a friction disc type or a variable speed control. And then there's also a belt and pulley system. These are, again, common older mechanical ways to change the speed of a system without a VFD. But remember, inverter about 92 to 98% efficient. We'll compare that to those mechanical variable speeds real quick. And actually the maximum efficiency you can get out of a mechanical variable speed friction disc is about 90%. As you change the ratio, as you change your ratio goes up, the output speed goes down, your efficiency drops off as well. So the maximum you can get is roughly 90%. So that's less efficient than the inverter right off the bat, no matter what you do. And the same thing for the belt and pulley option. It's a similar operating curve, where as the ratio goes up, your efficiency is going to kind of drop off. So they're not as efficient as the VFD, and they certainly can't make the motor more efficient like a VFD can. So inverter is going to be a little bit more efficient than a mechanical variable speed device, and that's not even including all the other benefits that we have I've been alluding to, and we'll get to now finally. Some of the good things the VFD can do for you and for your system. One advantage is you can, when you're ramping up to speed, when you turn your motor on, that's directly powered from an AC line. It comes up to speed, but there's a lot of work being done on that rotor. When you use an inverter, you can actually control that ramp and the amount of work that's being done on the rotor. And that's some energy that you can save in the system. You can see in the graphs, there's a significant reduction in the work on the rotor when you control acceleration electronically with the VFD. You can also save some energy on the deceleration side when you're stopping the load. And you may have heard of regenerative energy before. A motor and a generator are very similar in construction. And actually, when you decelerate an AC induction motor, it acts like a generator and it pumps energy back into the variable frequency drive. Now, what you do with that energy, that's up to you. Sometimes you can have a brake resistor where it just burns off that energy in the form of heat, but that's pretty wasteful. What you could do is maybe have two inverters coupled together via the DC link. If one is starting and the other is stopping, that's a perfect chance right there to save some energy. With the deceleration of one unit, it acts like a generator and pumps energy into the DC link between the inverters. And the other drive can actually use some of that energy to accelerate. And that's when you need the most energy in an application, is during the acceleration. So you could actually recover some energy losses if you couple the DC links together, or if you use maybe a regenerative power supply. And the way those work is when your motor ramps down and acts like a generator, pumps energy back into your VFD, that energy can be sent to a regen power supply, which conditions the energy and sends it back on the line. And that way it's not wasted, or it's not burned off as heat as well. Those regen power supplies usually, they're usually at a premium, especially here in the US. They can be expensive, but if you look at the long-term goals and the long-term gains you can achieve with them, they can absolutely be worth your money. Another thing that a variable frequency drive can do for you is, if you take a look at this system, we have a variable torque load, which could be a pump or a fan, anything that changes the amount of load as the speed changes. These torque versus speed curves are for a two-speed motor, actually changing between the poles when you operate. And this is a typical way to control the speed before frequency inverters came along. If we look at the same system being run by a frequency inverter, there's a different torque versus speed curve for each speed set point. But what is very interesting is, we look at this, for every speed that's lower than the design speed of the motor, the way the load curve is shaped, the motor is actually very underloaded. And when the motor is underloaded, we'll explore a little bit more when we talk about that in the next step. When the motor is underloaded, though, it's operating very inefficiently. So one of the things that we can do to increase the efficiency of the system by changing those torque versus speed curves. And the way we can do that is with the variable frequency drive, because I not only have the capability of changing frequency, but I can also change the voltage. So by changing the voltage versus the frequency output of my VFD, I can actually tailor the torque versus speed curve to more suit the application. For example, this variable torque load. Now for every speed set point that I'm running my motor, it's ideally loaded. I've lowered that curve to match my nominal torque rating of the motor at the speed that makes the system a lot more efficient. That's a lot of energy that can be saved there. So there are many ways to save energy in a system by using the VFD. And especially if you set them up correctly, they can easily outweigh the inefficiencies that are naturally added to the system when you add new components to it. Okay, so next, the next components we're going to talk about are the motor and the gearbox. We're going to talk about the motor first, but the majority of all losses are heat, but especially in the motor and the gearbox. In an asynchronous motor, we're going to have some of the same losses that we've had for any of the electrical components we've discussed. We're going to have copper losses, but there's a couple of different losses in an asynchronous motor. You have friction of the bearings, you can have iron losses, you can have eddy current losses, and you have a bunch of different losses, but really the main loss that we can attack are the copper losses. And we'll talk a little bit of how we can do that in an asynchronous motor in just a second here. Interestingly enough though, in a synchronous motor, that means a motor that has a permanent magnet on the rotor, there is no slip, so there are no copper losses in the rotor. So inherently, a synchronous motor is more efficient than an asynchronous motor. But for today's discussion, we're going to talk about the asynchronous motor since they are by far used more often and they are less expensive than synchronous motors. So there's just more of them out there, and it could make a larger impact in our conversation about energy if we discuss them today. If we look at the relative losses in an asynchronous motor, the majority of the losses are copper losses. If you look at those two big orange bars at the bottom, those are your losses in the stator and your losses in the rotor due to copper losses. That's the current flowing through the motor, creating heat, which is lost energy. There's a couple other things that you can see there, like the dark blue at the very top. Those are going to be friction losses from bearings. We could put high efficiency, low friction bearings in a motor, but in the big picture, that's not really going to make that much of a difference, but it can help a little. If we look at the other losses though, like copper losses, if we attack those areas, we can make a big difference. So how can we attack those losses and how can we change the efficiency of this asynchronous motor? Well, there's two major ways. The first way is to use better materials. A lot of synchronous motors have an aluminum squirrel cage in the rotor, and the aluminum has a little bit higher resistance than copper. So if you use copper, which makes a better conductor, it's a better material that you can make the rotor out of and reduce the amount of resistance by reducing the amount of I²R copper losses on that rotor. Now, second way we can make an asynchronous motor more efficient is by over-dimensioning it. Now, this may sound kind of weird, but let's think about it this way. Looking at this efficiency versus load curve, let's think about a car engine or a car motor instead of an asynchronous motor for just a minute. Your car is designed to operate at a certain speed, and most of the miles per gallon ratings in the US are based off 55 miles per hour. If you go faster than 55 miles per hour, you're going to use more gas. And if you go slower than 55 miles per hour, you're going to use more gas as well. But the big picture is that the efficiency of your motor changes at different speeds and different loads. The same is true for our asynchronous motor. If you look at the blue curve on the top, that shows how the efficiency changes with loading. At 100%, I have a certain efficiency, and then you can see the curve kind of change a little bit. Actually, it really starts to dive down when the motor is fairly underloaded. And that's one of the things we were talking about from earlier with the inverter. And underloaded motor is less efficient than a properly loaded motor. So what we can do is we can take, let's say, a motor that's rated for 5 horsepower, and that would be 100% load in our rating. It has an efficiency of, let's look at this curve here and say about 85% is a good number for it, for a regular standard efficiency motor of that size. If we were underload that motor, if it was rated for 5 horsepower at 100%, what if we lowered it to about 60 or 70%? What happens to the efficiency? Well, if you look at that curve, you can see the efficiency. If you back off from 100 to about 60 or 70%, the efficiency actually goes up a little bit. So what we do is we have the motor that's capable of, let's say, 5 horsepower, but we rate it for 3 horsepower to try and get into the sweet spot where the efficiency is a little bit higher. Now we have a more efficient motor. That means it's not going to be, we're not going to have as much heat loss because that motor's not working as hard. And that's the main sources of losses that we're trying to avoid, is those heat losses. So how does increasing the efficiency affect the motor? Well, a couple of different things. If you use copper instead of aluminum, it's going to be heavier. Copper is heavier than aluminum, so the rotor inertia goes up, and copper is more expensive than aluminum, so pricing is going to go up too. The rotor inertia is going to go up with the over-dimensioning motor because the inertia is actually more affected by the size and shape of the component rather than the mass, because the size has a squared effect on inertia. So there's a couple of different things that are going to change. Our inertia goes up, so we can't start and stop the motor as fast or as often without it heating up. It's going to be more expensive, obviously, and the thermal utilization is going to go down. So different things are affected, but remember, back in the first section when we were talking about the relative potential difference we can make in changing components and saving energy, and by using a high efficiency motor, I told you there was something about 10% or so, and using the VFD, we could gain 30%, and in mechanics, we could stand to gain roughly 60%. Well, if using the induction motor that's of higher efficiency or a premium efficiency, if I can only save 10% the overall energy of my system, is that worth it? Is it worth doing that? Well, one of the other things you have to think about is in an asynchronous motor, there's only two moving parts. It's two bearings and that's it. They're a very solid construction and it's a very simple machine and they last for a very long time. They last very long. Larger motors can last up to 20 years. So in my opinion, it is worth it to have an increased efficiency motor in your system because of the lifetime of the motor. You're going to save so much energy because of about 96% of the lifetime cost of an AC induction motor is the used for energy just to run that motor. So you can imagine how much it would cost to run a 10 horsepower motor for 24 hours a day, 365 days a year. And we'll actually go through a couple of those calculations later. But even though it's a relatively smaller portion of the gains that you can make, it's still worth doing because of how long these motors last and how long they are part of your system. Again, most of the energy cost is in running that system. So making an increase in efficiency there is only going to help you. So when should you use an energy efficient motor? Well, you're only going to be able to save energy if you're running. So if it's going to be a motor, so it's going to be on a motor that you turn on and it's running all day or runs for a long period of time. It's going to be a motor that doesn't cycle. You turn it on and let it run S1 duty or continuous duty. You don't want it to be loaded, or you do want it to be loaded properly. And remember, we were looking at the inefficiency versus loading curve just a few minutes ago. If it's really underloaded, your efficiency really goes down and you don't want that. So you want it to be proper loading conditions. You don't want to have it cycling back and forth all the time. And you want your application to turn the motor on and just kind of let it run. The longer it's running, the higher chance you have to save money. And when would we not want to use one? Well, of course, the exact opposite. If the utilization is bad, like the motor is really underloaded, if you're starting and stopping that motor all the time, or if you have a low number of operating hours, if you only run this motor for 15 minutes, half hour or an hour a day, when are you going to end up gaining the money back that you put in on your initial cost for the motor? It's going to take a long time for the amortization to occur, and it's not going to be worth it for you. So you also need to know when you shouldn't use an energy efficient motor. All right, the next part of the system we're going to talk about is the gearbox. And this is a really big part of the system, and this is where we can stand to make a lot of gains in our efficiency. Some of the losses in the gearbox are going to be churning losses and mesh losses, and that's where the teeth actually come together. And we can also have windage and seal losses. There's other losses too, but we're just going to concentrate on the ones that we can really make a big difference with. If we look at the proportionality between the different losses in the gearbox, the majority of the losses come from the actual tooth contact or the meshing. And we also have churning losses and we have bearing losses and seal losses. Seal losses, they can be minimized a little bit using the correct amount of lubrication. Bearing losses, they can be minimized a little bit as well by using low friction bearings, but more importantly, the proper amount of lubrication. If you put too much lubrication or too much grease in a bearing, you're going to make it really inefficient. So those are a couple of ways to minimize your seal and your bearing losses. But let's focus on the big loss in the gearbox, and that is the mesh power loss or the tooth contact loss. So we'll classify gears into two major categories, and I know there are many more categories than that, but for us today, it's good enough to talk about a rolling type of contact teeth and sliding type of contact teeth. Rolling type of contact would be like a spur gear or helical gear, bevel gear or helical bevel gear. This type of contact is much more efficient than sliding contact, which would be something like a worm gear. Rolling contact gears typically have power loss of about 1.5% per stage, and that's pretty good. A worm gear's power loss is actually dependent on a couple of different factors. the ratio, and how many teeth are on the worm gear itself. The efficiency of a worm gearbox is inversely proportional to the ratio. So as that ratio goes up, your efficiency is going to go down. If you just want to compare rolling contact versus sliding contact, a sliding contact gear, like a worm gear, is going to be much less efficient. It's going to run a lot hotter, and there's a lot more friction. There's a lot more surface contact, and there's a lot more losses. If you pick rolling contact type of gear, you're going to have a much higher efficiency. You're going to start to save a lot more energy. So rolling contact gears are a lot more efficient than sliding contact gears. And while we're talking about gear contact and efficiency, just briefly want to talk about synthetic versus mineral oil. Very quick. Synthetic oil is designed to have lower traction coefficient, and that means the oil wants to stick together very well. So when you have the teeth come together and the oil is in between the teeth, the oil doesn't shear apart. You want metal, oil, and then metal again. You don't want metal on metal contact. And that's something that synthetic oil helps you to avoid inside your gearbox. So that lowers the amount of friction inside the gearbox, and friction is what? Friction is heat, and it also lowers the noise that you have in your gearbox. So synthetic oil helps to increase our efficiency a little bit. Well, how much does it increase our efficiency? Well, we were talking about rolling contact gears just a couple of seconds ago. We said about 1.5% of power loss per stage. Well, if we use synthetic oil, we can get rid of about 30% of those losses. So we can reduce the amount of loss per stage from gearing down to 1% per stage. And that's pretty significant, a 30% reduction in gear friction losses per stage. Now, what does a 0.5% really give you? Because it doesn't sound like much. But let's take a typical gearbox, for example. Let's say a 10 horsepower motor with a 3-stage helical bevel gearbox using mineral oil. That is shaft mounted. You can see in the calculation up here, 75,394 kilowatt hours per year is about how much energy you're going to use just to run that. And that would end up costing roughly $7,539 for the year, assuming at 10 cents per kilowatt hour, just to run that gearbox with mineral oil. Now, that extra 0.5% of energy that you're saving, check it out with the different oil. Synthetic oil with the same motor turning the same gearbox now only takes 74,222 kilowatt hours per year to run. And you can save a lot of energy by switching your oils. You can actually end up saving a lot of money too. You can save about $117 per year just with this one particular unit. I mean, what if you have 10, 20, or even 30 of these units in your plant? You know, that adds up to a lot of energy savings. And of course, saving energy also equates to saving money. One of the other benefits of synthetic oil is you can increase the life from 2 up to almost 5 times the life of the oil in some cases. So that means you don't have to change oil as often. You don't have to buy oil as often. You don't have to do preventative maintenance as often on your gearbox. And so there's another hidden savings within synthetic oil. Of course, the initial cost is more, but your long-term benefits like your efficiency and longer oil life are going to make up for that initial cost in the long run. It's going to be more efficient for you. Now, back to our gearbox losses. So, there's some other losses like churning power losses. Basically, churning is the gears have to plow through the oil, and that creates a loss. It creates friction between the gears and the oil. So there's a couple different factors that affect these churning losses. One is the size of the gear, one is the speed of the gear, and another is the viscosity of the oil. The gear type also comes into effect here. There's different types of gears, so all of these things affect the churning losses. One of the major contributors to churning losses is the mounting position. Now, the mounting position of a gearbox really determines how much oil you have to put in it. And the amount of oil is going to determine how much friction is between the gears and the oil itself. If a gearbox is mounted horizontally, as the gears dip down into the oil, they can carry oil up to the other gears that it's making contact with. If a gearbox is mounted vertically, you have to put enough oil in that to reach all of the gear sets. So there's really going to determine the amount. So that's really going to determine the amount of losses that you have with your particular gearbox. If you take a look at some of the measured values for a particular gear motor, a motor and gearbox combination, showing different efficiency levels for the different mounting positions, you can see the horizontal mounting position has the highest efficiency, and the vertical mounting positions have the lower efficiency, depending on if your high-speed pinion is completely submerged in the oil or not. That's just another really, it's not really a trick, but it's another thing that really affects efficiency in a gearbox, how it's mounted. So it can play a great part in your efficiency of your system. We have one more piece to the puzzle, and that's the mechanical component. After the gearbox, it's attached to a transmission element. There's a couple of different things you can have. You can have a belt, you can have a tooth belt, you can have a chain, or you can have you can be directly coupled with a shrink disc or a tapered bushing shrink disc style mounting. There's different styles of transmission elements between your gearbox and your application, and there's going to be losses there. You're going to have friction, you could have stretch, you could have slip if your belt doesn't have any teeth. So of course, that's probably going to be our worst choice for a transmission element, something like a V-belt. A V-belt is going to have the worst efficiency because not only do you have stretch, but you have slip, and slip creates a lot of friction, and friction is heat, of course, and that's lost energy. So we don't want to do that. Chains and tooth belts are the best when it comes to having some type of external gear reduction other than a gearbox. But the best way is to go with a direct mounting using a shaft mount, because you're going to transmit 100% of the torque and you're not going to have any losses like you would with a belt or a chain. So the best way is always to go direct mount between your gearbox and your application, if that's at all possible. Now we've talked about all the different components of the system. Let's just recap everything real quick. We have a total system efficiency. All of the efficiencies of the individual of each individual component are multiplied together. So each little change in efficiency, each power loss makes a big difference in the overall operation and performance of our system and how much energy we consume. So the efficiencies are multiplied together, and we can take a look at that in a real live system. This is a real example that we had with one of our customers who was using a motor with a V-belt and a worm gearbox. And that was turning the chain, and which in turn was turning a conveyor. And what we did was convince this customer to go with a right angle helical bevel gearbox. It was more efficient, and we could directly mount that gearbox right to the machine. We could get rid of the transmission elements, and we can increase the efficiency. So look at the efficiency of the system at the top with the worm gearbox. All of those efficiencies multiplied together, 60.8%. Almost 40% of energy that we put into the system was lost to heat. That is very unfortunate, since you pay for it, or you will end up paying for that energy. If you look at the bottom though, all we did was take the same motor and put in the right angle helical bevel high efficiency gearbox, couple that to the same conveyor, and the efficiency went up to 88%. That's a big difference. And to put things into perspective, that system at the top is about 7.4 kilowatts that was lost due to its inefficiency. How much is 7.4 kilowatts? Well, 7.4 kilowatts is enough to power 123 60-watt light bulbs. That's a lot of energy and a lot of heat and a lot of light, a lot of waste too. That could really be taken care of by maximizing our efficiency with each individual component, removing components when they're not necessary, and optimizing the whole system, thinking about the whole system. Now, of course, the worm gearbox was cheaper initially, but if you think about it in the long run, it was much more expensive choice for that system. When you think about the total cost of ownership, the initial cost is about 20% of your total cost of the system. So your follow-up cost, that's where you're really spending all your money. And the majority of the follow-up costs, about 90% of your follow-up costs, is the energy, because you buy that system. It doesn't just run for a couple of days. You have it for years, and it runs every day. So each small increase in efficiency is going to save a lot of energy in the long run and a lot of money. So I thank you for your attention today, and I believe now we should have some time to answer a few questions.
Please don't leave us now. It's time for the question and answer portion of the session. Immediately following the presentation, click to the next section to move on to join the live Q&A. So these details can also be found in the Additional Resources tab on the left side of the screen. Please submit your questions using the Zoom question and answer interface, and we'll start that momentarily. Thanks very much.